Good morning. In this video, we're tasked to find the current passing through each resistor in this circuit. Now, let's examine the circuit. We have two voltage sources here. One is 15 volts and the other is 20 volts. We have five resistors here. We have 8, 9, 5, 4, and 7 ohms. And we need to find the current. Let us recall Ohm's law. Ohm's law states that voltage equals current times resistance. Since we're trying to find the current, maybe isolating current may be easier. So current is voltage over resistance. So if we have voltage and resistance, we can find this. Now, let's look at the circuit. If we ignore this one, this would be a series circuit with 8, 7, and 9 ohm resistors and a 15-volt voltage source. We can use the mnemonic here for a series circuit. So the voltage in a series is sum, and then current in series is equal, and then resistance in series is sum. While in parallel, this is equal, sum, and harmonic. I explained what all of these mean in an earlier video, but what you need to know is that currents in series is equal to each other. What that means is whatever the current here, here, or here may be, they're all equal to each other. All right. In this simplified circuit. So we can find the total resistances, we have the total voltage, and then we can use Ohm's law in order to find the voltage. But it's not so easy since there is another voltage source on the other side and it's more complicated than that. So maybe we can use something else. First of all, let's discuss Kirchhoff's voltage law. Now, Kirchhoff's voltage law says that the algebraic sum of the voltage source and the voltage drop should be equal to zero. So the voltage source, this is the voltage source. It comes from the batteries in here. And the voltage drops in these resistors should be equal to zero if you add them all up. Now, the voltage drop is a negative quantity, so it should be negative. Then the current, since this is a series circuit, should be equal all of them. So it's just the current. So this current and this current are all equal to each other. So we multiply the current by the resistance of each resistor. So R1 or R2 or R3. Uh, you need to add them all up in order to get the sum of all voltage drops. So you can replace this one with this one. So the sum of all voltage sources minus the sum of all uh, current times resistance equals zero. Or if you transpose this to the other side, sum of all voltage sources is equal to sum of I times R. So it's going to be useful later on. Now let's discuss next Kirchhoff's current law, which states that current entering a node, this is a node, is equal to the current exiting a node. So a node is when branches of the circuit meets in one point. So for example, maybe this is our circuit. This is the one that's entering. This is the one that's exiting. So there's two exits and there's one entrance. Maybe there's another one that enters. I don't know. Up to you. But that's again, this I entering is I exiting. In this example, I1, I2, if you add them together, it should equal I3, I4. In the example, 3 amperes plus 2 amperes is 5 amperes entering, and then 1 ampere plus 4 ampere is 5 ampere exiting. So this fulfills Kirchhoff's current law. So we're going to be using these in order to solve this one. How will we use Kirchhoff's voltage law first in order to find anything here? So let's let's establish loops. So Kirchhoff's voltage law wants a series circuit, but there's two different circuits here, and it's messy and whatnot. Is it a series circuit? Is it a parallel circuit? It's kind of complicated, but if we did ignore this one, that's just a series circuit, right? So we can say that we have a series circuit here. Let's name it I1. So loop I1. Now we can ignore this other line. So let's include calculations here. So this is another loop, loop I2. Now, the directions of the loops are just implied. We assumed the directions of the loops, but how can we intelligently assume the loops where what direction it goes? Look at the voltage source. The voltage source here is positive on top, then negative on bottom. Now, if you know a thing or two about batteries, is that when we have positive and negative here, the electrons move out of the negative and move into the positive. So it creates a circuit where it just does this. So electrons go from negative to positive. So the flow of electrons is opposite the flow of current. So flow of electrons is opposite the flow of current. So in current, we go from negative to positive. In here, the arrow here states that we need to go from negative to positive. And like in here, we also need to go from negative to positive. So that is the direction of the current going here, and that's the direction of the loop. Let me delete this one. So that's how we got the loop directions. Now, after we get the loop directions, we can set the current directions. The direction of the current passing through each resistor, because the current loops is not exactly the resistor loops. You can use Maxwell's mesh law, which is another technique, but we will be using Kirchhoff's voltage law for this one, so that if you mind. So if we look at this, I1 passes through this, and this. So I1 passes through here and here as well as here. I2 passes through this one, and also this one. So we have I1 and I2 here, and then we have a combination of I1 and I2 passing through the 7 ohm resistor. So we have three unique currents going through here and going through here. They have the same current. Going through here and going through here, they also have the same current. Going through here or here, I don't know which direction it goes through, but let's just assume it goes down. It's another current. So let me clean up the inside of this for a moment. All right. So let's name all of these currents. So let's name the current that goes through 8 and 9 ohms, I1. Let's name the one that goes to 5 and 4 ohms, I3. And let's name the one that goes to the 7 ohms, I2. Don't worry about which one is which. I1, I2, I3. It's just convention and to go left, right. So I1, I2, I3, we have three variables. We need three equations in order to solve it possibly, using a calculator or maybe or by hand. We will see how it goes. So let's focus on I2 and let's use Kirchhoff's voltage law. So Kirchhoff's voltage law says that the sum of all voltage sources is equal to the sum of I, which is the current, times R. Okay? So sum of all voltage sources in loop I1, ignoring everything in this one, so just focusing on what loop I1 encompasses. 15 volts is here. That's the only one, so equals. And go, it's the current flowing through 15 volt voltage source is agreeing with I1, so it's positive 15. Let's just put a plus here so it indicates positive. And the currents that are connected with loop I1 is current I1 and current I2, right? Look at the directions. The direction of this is agreeing with I1, so it's positive. The direction of I2 is agreeing with I1's, loop I1, so it's positive as well. And let's list the resistances that are affected by the current I1. So this also has current I1, so it's 8 ohms plus 9 ohms, right? And for I2, we have 7 ohms here. So we have our first equation. Second, so let's focus on I2. Let's do the same thing. So the direction of I2 and the 20 volt is agreeing with each other. So let's say it's 20 volts. It's positive 20 volts. The loops that we have here is I2 and I3. Not the loops, the current, sorry. The current that agrees with, no, that is associated with loop I2 is current I2 and I3. I2 does not agree with the direction of loop I2. It goes in different directions, so it's a negative quantity this time. Uh, 7 ohms. Now, why isn't it positive? Well, it's just because it's going in a different direction than loop I2. So we have to make it go negative. It's against the flow of current in I2. Again, I2 is just what we assumed the direction I2 is. It might be wrong. If I2 turned out to be negative, well, it means it's just going in the other direction. Same with I1 and I3. If the currents are negative in our result, it just means it just goes on the other direction than what we thought initially. So that's why it's negative. And for I3, it's going the same direction, so it agrees, so it's positive, and the resistors are 5 ohm plus 4 ohms. So this is equation 2. Now, for our third equation, you could use the Kirchhoff's voltage law to encapsulate all of this, ignoring the 7 ohms. So uh, uh, maybe it going that way, but that's too work. That's too much work. So what we're going to do is use Kirchhoff's current law. Where exactly? On this node. Look at what this node represents. I1 goes in, I3 goes out, I2 goes out of it. So we can say, let's this simplify this. Look at what goes in the node, I1, from here. I1 goes in the node, I3 and I2 goes out of the node. So Kirchhoff's current law states that I1 equals I2 plus I3. Let's move everything else on the left side. So I1 minus I2 minus I3 equals 0. That's going to be our third. Now, let's arrange our three equations together. So, so for the first one, let's go back. 17I1 plus 7I2. So, 17I1 plus 7I2. Let's leave a space for I3 because there's no I3 in that one. So 15 volts. This is one. For 2, we get negative, since there's no I1, let's leave space here. Negative 7I2 plus a 9I3. This is equal to 20 volts. For Kirchhoff's current law, the third equation says I1 minus I2 minus I3 equals 0. Now you can remove the volts here since this is just numerical analysis. But for now, so you can solve this using handwritten methods like adding and subtracting all of this, but it would be too much work because there's a lot of numbers that aren't good, and this is probably not an integer, but we will be using a calculator. I have here a Casio FX991 ES Plus. I think it's banned in like board exams, but it's it's similar enough to other calculators that we will be using it. Maybe you have other calculators, but Casio is good. Not sponsored. So, if you have a Casio like I have, you can press mode and then 5 for equation, and then you can press 2 in order to find the uh, the simultaneous equation since three variables display, it would look a little bit like this. So there's A, B, C, and then D here. And then one, two, three. This for equations one, two, and three. All right. If you have another model, you may find it under systems of equations, simultaneous equations, or in this case, it was ax plus by plus cz equals d. You can find it anywhere like that. Go study your calculator. It will be useful for you if you're an engineer. So, uh, how can we input all of this? We'll look at here. So let's say A is I1, B represents I2, and C represents I3. We just need to find the coefficients of I1, I2, I3, and then D is just a constant, so it's going to be this one. So I1 is 17, this is 7, and C, since I3 doesn't exist here, it's just 0. Basically, there's a 0 I3 here, plus 0 I3, but we don't write that usually. And then D is 15. Let's just input everything here. Then there we go. So we've inputted everything in here. You should be able to get three answers for I1, I2, and I3. So according to the calculator, and round enough to three decimal places, so is more accurate. I1 is 1.134 amperes. I2 is negative 0.612 amperes. I3 is 1.746 amperes. That's interesting. I2, which we assumed was going downwards, is actually going upwards. So our assumed direction was wrong. That's what the negative means, right? So don't worry about the negative answer. It just means it's going in the opposite direction of what we assume. So how do we know this is correct? Well, we can check again using Kirchhoff's voltage law. So let's go again to a simplified version of the circuit there, and another one. All right. So we have 8 ohms, 5 ohms, 9 ohms, 4 ohms, 7 ohms, 15 volts, and 20 volts. So let's use Kirchhoff's voltage law. So 15 volts on one side and on the other side, 8 plus 9, since I1 affects this one and this one. No, I1. I2 affects this one and I3 affects this one. Let's put the directions. This goes here, this goes that direction, and this goes that direction. But this one goes in this direction and that direction. So 8 plus 9, then I1. Since I2 goes in a different direction, we should subtract it. So minus I1. Let's put the true value of I1. So 1 point times 1.134 amperes. So it's like 9 ohms. So there we go. Minus 7 ohms times 0.612 amperes. Let's try calculating it on my calculator. So 8 plus 9 is 17 times 1.134 minus 7 times 0.612. That is around 14.994. You may ask, why isn't it equal to 15? Well, because we rounded off to three digits. And seeing as there's like, this is the only discrepancy, the third digit. If it's like 9, like, and then 9, it would be so super close, right? So there's only a difference of 0.06. No, 0.006 actually. It's much more impressive. So it's just rounding error at this point, and we can accept that these values are true. Now let's try the other one if you're not convinced. So this one goes I3. I3 is 1.746 amperes. Then we multiply it by the resistances that are affected by I3, which is 5 and 4. And then ohms. Now, if you ask why I'm adding the resistances before multiplying it, it's the same as multiplying each resistance and current separately, but I just simplified it in order to look better. And the third one, since I too is agreeing on the direction of this loop, we can finally say that this is positive 7 ohms multiplied by again 0.612 amperes. Test that. So 9 times 1.746 plus 7 times 0.612 is equal to, oh, this is so close, 19.998 volts, which is close enough that it can be brushed off as rounding errors. And I think we've finished calculating all the resistances for each circuit. Again, I1 is represents the 8 and the 9 ohm currents. I3 represents the 5 and the 4, and I2 represents the 7 ohms. So we've completed our job. So thank you for watching, and I'll see you in the next video where hopefully we'll do some differential equations, but I'm not sure when that will be finished. Bye bye.